Going to solve this problem. Diameter of binary tree. Given the root of a binary tree, return the length of the diameter of the tree. The diameter of a binary tree is the length of the longest path between any two nodes in a tree. This path may or may not pass through the root. The length of a path between two nodes is represented by the number of edges between them. So here you can see the input and the output is 3 because 3 is the length of the path, 4, 2, 1 and 3, or 5, 2, 1 and 3. And if it's 1 and 2, it's like only 1 because it has only one edges. The length of a path between two nodes is represented by the number of edges between them. Here we have like 3 edges, 1, 2 and 3. So I'm going to start coding now. So first I would like to say that I would like to talk about possible approaches. Here, so we could use a recursion solution. For each node, we can compute the longest path passing through it by summing the height of its length and left and right subtrees. We can recursively compute the diameter of the left and the right subtrees, return the maximum of the path through the current node, that is the left height and the right height, and the diameter of the left tree, the diameter of the right tree. And for this we can go about like first we need to compute the height of the left subtree, then we need to compute the height of the right subtree, then compute the path through the node as left height plus right height. Then we need to recursively compute the diameter of the left and the right subtrees, and we need to return the maximum of the above values. So that's the algorithm we have, and the time complexity is, so computing the height of a tree with n nodes take O of n. So for each of the n nodes, we compute the height of its left and right subtrees, each taking O of n in the worst case. So the total would be O of n plus n, that would be O of n square. And the space complexity is that the recursion stack for the diameter computation O of h, where h is the tree height, O of n for a square tree, or O log n for a balanced tree, and additional recursion stack for height computations, we need to consider that. So typically I would say it's O of h in the and O of n in the worst case. And so yeah, the drawback here is that we need to repeatedly compute heights for the same nodes, which is very inefficient. So we can think about approach 2, which is optimized recursive solution. Here we can use height and diameter calculation. So instead of computing the height separately, we compute the height and the diameter together in a single recursive pass. For each node, compute the height of its subtrees and use it to calculate the path through the node. So we track the maximum diameter seen so far using a global or class variable. So the algorithm, this would be that we can say that we can define a helper function that returns the height of a subtree rooted at a node. In the helper function, we can recursively compute the left and the right subtree heights, compute the path through the current node as left height and right height, update the global maximum diameter if the current path is longer, and return the height of the max current subtree, which is max of left height and right height, plus 1, and then we need to call the helper function and return the maximum diameter. The time complexity would be that each node is visited once. At each node we perform constant time operations, and the total would be O of n, where n is the number of nodes. And the space complexity would be that recursion stack depth is equal to the height of the subtree. Total would be O of h, where h is the tree height, and O of n for skewed tree, O of log n for a balanced tree. So here we have the advantage that we can avoid redundant height calculations, and it makes it much more efficient. So I'm going to write the code for the optimized solution here. Here we are computing the height and updating the maximum diameter, and then we return the maximum diameter. So the height of the null node would be 0. Now we can recursively compute the left and the right subtree height. So we are saying int left height, that would be height of node dot left then we need to path through the current node, which would be left height and right height. So the maximum diameter is going to be maximum of these values. As I explained previously, the maximum diameter left height plus right height. And then we are going to return math.max, maximum of left height and right height. So we are going to return the height of the current subtree. So this is going to give the height of the current subtree. Okay, this looks good. So you can wonder why I'm using a class variable here. It's basically because the helper function, it returns the height, but we need to track the diameter, that is the path's length. So by using max diameter, we can update the diameter at each node without altering the return value of the height function. So here we don't have to alter the return value of the height function, but we can update the max diameter at each node. And yes, as I mentioned previously, the time complexity would be O of n and the space complexity would be O of h, because the recursion stack depth is equal to the height of the tree, and so it's h is O log n for a balanced tree and O of n for a skewed tree. And here you can see that I've handled the edge cases for an empty tree and a single node. If the tree has only one node, the left and the right height are 0, so maximum diameter would be 0. That would be it would have no edges. And for a skewed tree, it works correctly as a recursion processes each node and the maximum diameter captures the longest path. That is example n minus 1 for a chain of n nodes, and for a balanced tree it efficiently computes the diameter leveraging the recursive structure. So if we want to avoid using the class variable, we could use a pair of values like height, diameter, and from the height function using a custom class or an array. But this could complicate the code slightly. And so what if we need the actual path and not just the length? We could modify the solution to track the nodes in the longest path, possibly by storing the path endpoints in the helper function. And so can we solve this iteratively? Iterative solution using stacker queue is possible but complex, because we need to mimic the post order traversal and track heights. A recursive solution is more intuitive.